So today what I will try to do is to give the basic geometric ideas that underlie F-theory, given that it's one of the approaches of string phenomenology in which some recent ideas have been put forward, in particular of how essentially to combine some of the, what you could call perhaps virtues of the brain approaches to making four-dimensional theories where essentially one can focus on open string degrees of freedom without worrying immediately about things like moduli stabilization that I discussed earlier, but at the same time have the power essentially similar to the hydraulic string where one can rather naturally obtain gauge groups that incorporate grand unification and things like that. But it requires a perspective on string theory that is essentially non-perturbative. And I've mentioned this a few times, that the connection with string theory and non-perturbative physics goes via theories that have mysterious names like M theory and F theory. But again, today we'll take the F theory perspective, but it's intimately connected also with M theory. But now 12 is already a pretty big number, so we better keep, it's more than the number of fingers on our hand, so we have to keep track of all our dimensions. So let me just make a little table of where all those dimensions go, those 12 dimensions. I could give them a name, say 0, 1, 2, 3 is the space-time dimension. So at least those we can easily imagine. And this is eventually where the effective quantum field theory will take place that we're going to build. And all the other 8 dimensions basically are geometrical tools for building that particular effective field theory in a way that hopefully will give us also more insight in what the possibilities of the 4D theory are. So rather arbitrarily, okay, there we go, 4, 5, 6, 7. That will be a next natural group in terms of the 4 dimensions. So I put 4 here, plus 4, and then we'll add up to 12. And these will be the internal dimensions. And the internal dimensions of a 7-brane. Because the matter will, in F theory, will rather naturally live on a 7-brane. So this is 7 plus 8 dimensions. So then we have dimensions 8 and 9, which I'll give a name. At least let's use a complex notation. So this is one complex set of coordinates. So these are transverse dimensions. So the fact that they're transverse to the 7-brane, so those are the 2 remaining dimensions orthogonal to the 7-brane world volume. And the last 2 dimensions, maybe I will not even give them a name. They represent a torus of a shape parameterized by tau. These things are called, this is called the elliptic fiber. What all those 12 dimensions are about is to keep track of how this thing in particular depends on those 2 coordinates. It can do maybe a few more other things, but for now we'll mostly be focusing actually on these 4 dimensions here where we just look at what happens transversely to the 7-brane and we'll keep track of how this tau parameter, which I mentioned before, is connected to the axion and the dilaton in this particular way, how that thing will depend on the 4-dimensional coordinates. Now, the fact that the string coupling constant will depend non-trivially on the internal dimensions automatically means that a part of the perspective that we'll have will be non-perturbative, because GS will be forced at certain places to be bigger than, considerably bigger than a small number of order 1 or even bigger. One of the important tools that we'll be using is this notion of S-duality that has to do with the fact that the physics in the end should not depend on the way we parameterize this torus, and different parameterizations of that torus are associated with what we call SL2Z transformations, where tau goes to A tau plus B, C tau plus D, with A, B, C, and D integers. So we'll keep an eye on those type of transformations, yeah, this automatically will mean that we have essentially a non-perturbative perspective on this theory. Are there questions at this point? This is just setting the stage, but it's important to know where we are. Yes?
Just one question, maybe you can answer it later on, but when you're talking about non-perturbative string theory, then when do we believe it, or when do we know what's going to be valid if it's not perturbative?
Okay, so the main principle that we'll be using in at least what I'll be using today. So the question is, indeed, if it's non-perturbative, how do we actually really know, how do we have control over what we're doing? And it's true that it's hard in a regime in F-theory to have quantitative control over quantities that would not be protected by some supersymmetry or by some holomorphy. So that's one remark. Another important principle that we will make use of is that even in a non-perturbative setting, you can sometimes identify which degrees of freedom become light. And then a principle that we assume is that those degrees of freedom that become light indeed should become fields in our low-energy effective Lagrangian. In perturbative string theory, the things that become light are short strings. Whereas here, they might be, among other things, D strings or objects that we typically think of as being heavy. And the reason why D branes are thought of as being heavy is because their mass is proportional to 1 over GS. In GS, we typically think of as being small, but in regions where GS suddenly gets big, then those kind of objects can become very light, and they will become part of the low energy spectrum. So that's the sense in which, yes.
So the only non-perturbative formulations of string theory that I'm familiar with are, one is matrix theory, and the other is whatever the dual equals force creating duals.
Mm-hmm.
But those are very background specific. And I mean, when you say perspective on 2D here, I mean, are you saying you have something as precise as that?
No, not at all. So I think I gave it's essentially the same question. So what I'm saying is that in the end, there's no non-perturbative real complete definition of this. Also, M theory, indeed, apart from matrix theory, which in special backgrounds indeed can do some things for M theory. But as I said, the principle that we're going to make use of, which has been, again, tested in similar ways as these other dualities that you mentioned have been tested, is that what I just mentioned, that in certain corners of parameter space that we should definitely expect that certain degrees of freedom become light. And then we have some general, often also topological arguments for how those degrees of freedom should interact with each other. And the thing that I'll be focusing on today is really, okay, where does the non-abelian gauge symmetry come from? Or what might be the charged matter content of our theory? And those things can be determined basically on geometrical grounds without having perturbative control over the theory, and simply knowing that those degrees of freedom are there in corners of the parameter space where we do have perturbative control.
So, for example, are you assuming that you have some control in field theory and you just don't know what it is?
Okay, so if you pull it all the way back there, then actually we put ourselves in a pretty strict corner. It's true that for general F-theory backgrounds, it would definitely be hard to write down the worldsheet string theory. And so in that respect, I should definitely stress this. Indeed, before 94, 95, in string theory, we had a rather rigid point of view of what might be consistent string backgrounds. And indeed, that you want to be able to quantize the string in a certain background, and then you might argue that it's finite, etc. But one of the lessons that was really learned in 94, 95 is to say, well, actually the gravity, and especially after Polchinski introduced the D-branes, gives you hints of all kinds of other objects that are part of string theory, and we definitely have to take them into account in our thinking. And then one of the things that F-theory does, and this was preceded by ideas about the conifold, about certain non-perturbative degrees of freedom that suddenly can become light in a certain range of parameters of the theory. And then what you learn is that the degrees of freedom that become light, this is also what n equals 4 Young-Mills theory should have, is that if I take the n equals 4 Young-Mills coupling to be very large, then all the monopoles become lighter than the charged particles, and therefore the monopoles should be the fundamental degrees of freedom in which we're going to describe that region. And the S-duality conjecture is that that dual description actually looks exactly the same as the original description. And 2B string theory has the same self-duality in the sense that if I make this change in the 2B string Lagrangian, then all the, or at least there's not such a thing as 2B string Lagrangian, but after making that change, you always go to that parameterization for which this combination is the smallest. So for a given tau, which could represent a strong coupled region, if I want to describe that particular strongly coupled region, I'm going to find integers a, b, c, and d so that this quantity is small, corresponds to a weakly coupled degree of freedom. And then the degrees of freedom in that frame, you can call it a duality frame, namely I'm going to use that parameterization where the string coupling is small, then the degrees of freedom in that corner indeed should be weakly coupled if they are strings, because GS is small. But from another corner of the parameter space, those same degrees of freedom would be D-branes, and those things interchange. And what's nice, for example, about this picture from M-theory that we talked about a few times is that you can understand this thing rather directly, and let me again mention this, is that if I take the M2 brane, so if I take M-theory on T2 and I let this thing shrink, then basically I get F-theory. So this also gives me 2B string theory, because the size of the T2 is a circle in the 2B string theory. And then one way of looking at all these degrees of freedom is that if I take an M2 brane and I wrap it around the A cycle of this 2 torus, this becomes a fundamental string. So we call this maybe an F1 string. But if I take an M2 that wraps in that direction, I hope I don't get the two cycles interchanged. I think I have them right. Then this becomes a D1 string. Now, both these actually have kind of a perturbative description. We know what a D1 string is in the regime where the F1 strings are weakly coupled, because these are strings on which open strings can end. But the conjecture is, again, that if G string becomes very large, these things initially have mass proportional to 1 over G string, but if G string becomes large, then these become lighter than those, and then I should be starting using these as my fundamental units, at least building blocks for this theory. So in general, by the way, let me just mention this because I'm going to make use of that later. I could have a membrane that wraps sort of around in a particular way, where M2 could be on a cycle, say, P times A plus q times b. So this is a one cycle, but it winds p times this way and q times that way. And this becomes what we call a p comma q string, which, if you like, you can think of as being a bound state of p fundamental strings with q d1 strings. And these things will actually play a role in F theory in the constructions that we're talking about, where sometimes one of these objects becomes light, and those things will then represent gauge bosons, actually. So that's the thing we should anticipate. But before we go there, let's go back to briefly to these 7 branes, which are the easiest ones because they don't involve non-perturbative physics yet. They're sort of the most perturbative objects because they are just indeed ordinary D branes on which open strings can end. So this thing is a magnetic source for this C0 field, meaning that if I put a 7 brane somewhere here, and by the way, if I put a 7 brane on my blackboard, the blackboard in most cases will correspond to this transverse plane, the ZZ bar plane. So I put, so here, this is the ZZ bar plane, and at some location Zi, I put a D7 brane. So if I go around that 7 brane with, and I keep track of this parameter tau, it will not come back to itself. It will actually pick up a unit of flux in a unit period in the C0 direction because this thing is magnetically charged. Another way of saying that is that the tau in the neighborhood, say throughout the blackboard, typically it would have a value I over GS because e to the minus phi is 1 over the string coupling. But near the location of the 7 brane, there's going to be a logarithmic singularity, which indeed has this multivalued behavior. One of the things that you notice indeed that if Z goes to Zi, that tau goes to I infinity, which in our case is actually good because it means that e to the phi, which is the string coupling, goes to 0. So the D7 brane itself location is a weakly coupled region of our space-time, of this space. So strings are weakly coupled down here in this background. Another thing that it means is actually that the fundamental strings become light, are the light degrees of freedom on the D7 brane. Okay. Now, this is only an approximate solution. One could try to ask, okay, well, what does the exact solution of the background of a D7 brane look like? And so for that, let me briefly go back to this type of transformations. So if I take tau, then this is essentially an equivalence relation among the various values of tau, because if I make this transformation, it seems that I'm drawing a different torus, but then you can just rearrange your coordinates that you actually recognize that a torus that's related in this way is actually just the same old torus. So this tau variable can be restricted to what we call the fundamental domain. And what this fundamental domain looks like in the tau plane is that the imaginary tau value of tau can always be bigger than 0. Let's call that tau 2. And you can put tau in between -0.5 and 0.5. And one of the transformations that you have here is known as the S-duality transformation, tau to -1 over tau, which also means that I can make the imaginary part bigger than that particular circle. So the fundamental domain, this is the unit circle, -1, 1. The fundamental domain is that particular region. So these are all the physically inequivalent values of tau, but any of the other values can be mapped on it via one of these transformations. Now, if you think about this particular solution, this is not really a solution. This is just a local behavior near the location of a D7 brane. Because, for example, this particular number here can get a negative imaginary part, and we don't want that. Tau shouldn't have a negative imaginary part. So there's a special function, which is the modular invariant function. And I'm not going to say too much about it. It's the J function. It's a function of tau. And if I define it on tau, it will have indeed different values in that fundamental domain. But every time I go to another value via that map, J doesn't change. So J is invariant under that particular set of transformations. And it turns out that the solution that you really get in that case can be formulated in the following way, that if I view, so this is a very implicit way of writing the solution, I'm going to give, rather than giving you tau as a function of z, I'm going to tell you that J as a function of tau is going to have a certain behavior in terms of z. And it turns out that if I can have some constant which will label that freedom of having a string constant, string coupling here, times z minus zi. So if that J function as a function of tau happens to be a linear function like that, then that will just give me a solution for the D7 brane. So this is an implicit way of giving the solution. I'll tell you a little bit more about that J function later on, but it's the unique modular invariant function that's single valued, that doesn't change its value under these transformations. I could tell you a little bit about the gravity solution associated with the D7 brane, but let me briefly skip that, and I might mention it a little bit later. Are there questions about this? Yes. Let me be a little bit more specific about what it will do tomorrow. In general, that thing, so in terms of string compactifications, all these 8 dimensions are going to be made use of, and combined, these 8 dimensions, the compact dimensions, including this elliptic fiber, will be this Calabi-Yau fourfold. And one thing that we'll be doing is that this 7 brane can wrap a 4-cycle, so it's a 4-dimensional subspace, we'll call that S, within that Calabi-Yau fourfold. And in principle, you could have many of those kind of 4 cycles within your Calabi-Yau fourfold. You could have many Calabi-Yau fourfolds. But what turns out to be at least a principle that will reduce the number of possibilities is the assumption that, so this was done in the work by Fava and collaborators, that if you take this 8-dimensional space, so everywhere there's this tau, so combined this is a Calabi-Yau fourfold, and then there's a 4-dimensional sub 4-cycle, and that's where we're going to wrap the D7 brane. And I'm drawing it like this because it turns out that the geometry will become more unique if you make the assumption that you can shrink this particular cycle S to a small size and essentially decompactify all of this. So what we're going to do, at least in the remainder of the story of the next few days, is focus on that particular region. But it's still what will happen is that this region here will be an 8-dimensional space, but of a cone-like region where S will be the region where the cycle where the D7 brane is. But for now, I'm just focusing on these directions which involve the Z and the Z bar, which are orthogonal to that D7 brane. Yeah, it's compact. So this would be compact, and the transfer space is non-compact. So I'll be looking at these two. So for today, focus your mind on these two things. This will be a non-compact space, but it's perpendicular. It's the transfer space to the D7 branes. The D7 branes will be compact. But the fact that the transfer space looks non-compact is simply because we make the assumption that this region can be thought of as effectively being far away from here. And in terms of four-dimensional effective field theory, what it amounts to is that we essentially assume still that there's still some decoupling between the field theory on here and quantum gravity, because it turns out that the strength of gravity is determined by the volume or the proximity of this relative to that. It's the same as the story with that Shamit Gashri talked about with the Planck brane. Essentially what we're doing here, this you can think of as being the Planck brane region. Although this doesn't need to be warped, by the way, but you can still have a similar type of philosophy that you send this thing off to infinity, sending off the Planck length to very large length. But this is just, I'm not going to talk about this today. I'll only be talking about what happens over here. When I say D7, I actually mean plus a generalization, because we want to be more general in order to get grand unified gauge groups. More questions?
So how much symmetry do you have in space-time?
Typically, you keep one supersymmetry if this whole thing is a Calabi-Yau fourfold. So the condition that this is a Calabi-Yau fourfold, again, follows from supersymmetry. And that's a similar type of condition as what in the hydraulic string leads to Calabi-Yau threefolds.
The other dimensions of the seven brane are in space-time, right?
Right, sure, yeah. So when I say these are the internal dimensions, the seven brane fills space-time.
So the Calabi-Yau fourfold breaks 1/8 of the supersymmetries. So that's the 1/8 of that is equal to 1.
Right.
And then in the world body of the D7 branes, along the space-time directions, how many supersymmetries?
It's still one supersymmetry. I should say, though, that the D7 brane, because of the fact that the D7 brane does something non-trivial to the tau, is that the D7 brane, at some level, the Calabi-Yau fourfold already tells you exactly where all the seven branes are. They're part of the tree. Normally, if you have a Calabi-Yau, you can say, well, I have a Calabi-Yau manifold, I can still throw a brane on it. But the D7 branes, they have back reaction, and they will essentially already tell you what the geometry of the Calabi-Yau is. So the two things are one and the same. So that will become a bit more clear as we go along now, because indeed, as was mentioned also sometimes, is that Calabi-Yaus can be given the form of equations in some high-dimensional complex space, and then the solutions to some nonlinear equation parameterize some curve. And indeed, what we want to do, and you can see that here happening already, is that we want to be able to write down this tau parameter as a function of complex coordinate z. So what's a clever way to do this? Yes, sure. Are you worried about back reaction here? Sorry, yes. It's not a singular point. It determines one of those. Indeed, it determines. One could say a point where the elliptic fiber is doing something special. That's right. Okay, that's a chicken and egg question, but it's true. Let's say it this way: it's true that the locations of the D7 branes are highly constrained, precisely by the requirement that this preserves supersymmetry and that this is a Calabi-Yau manifold. So at some level, you're right. The geometry that you're going to write down will determine where the seven branes are, rather than vice versa. Although we'll see in many cases that the location of seven branes are still free parameters, especially if I just do everything in a plane. Locally, I can move those things around. Globally, there will be restrictions. Okay, so another way to parameterize tau as a function of z, we can do the following. So So the torus is actually an elliptic curve, and an elliptic curve means that you can write down a particular equation. So we're going to have three complex variables, y and x and z. So these are two extra complex variables. But I'm going to write down one complex equation. So in terms of dimensions, I'm going to add one more complex dimension to this z variable, and that extra complex dimension is that 2 torus. There's an equation that typically that mathematicians like, which is known as the Weierstrass equation, that gives me a relation between y and x. But that relation between y and x, it's a nonlinear relation, will involve functions which can be polynomials in z. So for given z, this is one given equation that allows me to solve y as a function of x. Now, notice that this is a cubic equation, and if I include the point at infinity, this equation can have zeros. Or how should I say? This equation will have certain locations where the right-hand side is equal to 0, and those will be branch cuts in terms of solving for y. So since this is y squared, for every x, there are 2 values of y. So this is a double cover, if you like, of the complex x-plane, because I can choose the 2 solutions of y. And then if you unfold that particular double cover, you actually recover, if you think about this geometrically, this is actually a torus. So this is a two-dimensional space that looks like that. And it indeed will have a parameter tau that one can obtain if you know the values of f and g. But those formulas are actually a little bit complicated, or at least non-trivial, at least. So this is a torus with parameter tau such that this j function turns out to be of tau. You can express it in terms of that function f. I think it goes like this. It's 24 f cubed divided by a quantity known as delta. And delta is 4f cubed plus 27g squared. And this thing is known as the discriminant. Turns out that in terms of another function, modular function, which perhaps was mentioned in John's lecture, the eta function, dedicate eta function, for those of you familiar with that, this discriminant is expressed in terms of the eta function like that. Anyway, so the main point that you have to remember is that for a given function f and g as a function of z, if I now move around z, I will get a certain value for tau just by a particular relation. And this is one way in which we can parameterize what we call this elliptic fibration, where over the complex plane, at every point we have there's a torus that sits there, and the shape of the torus is changing with the location z. So this is a useful way of parameterizing things. Now it turns out that in order for the whole space to be Calabi-Yau, for example, this f and g have to satisfy certain requirements, that have to be sections of certain line bundles, but I will not go into that right now. So just for a flat space, this does it. Now, if this discriminant goes to 0, so the location where delta is equal to 0 is actually a rather special location, because then the torus is doing something funny. The torus degenerates. And what I mean by degenerating is that if it does something funny like this, if the value of tau does something funny, then actually this delta has a particular behavior And obviously, in this case, it goes to 0. But there are various ways, actually, in which a torus can degenerate. It could be that the A cycle shrinks, or it could be that the B cycle shrinks. So another thing that tau could do, in general, it could go to 0, in which case the torus goes like this. And there are many ways in which the torus can squeeze into a singular shape. So we'll be keeping track of that particular location as we go along. Okay, there are many more things one could, in principle, say about these kind of equations, but I want to keep it sort of essentially basic. But at the moment, we're just parameterizing the shape. So are there questions about this?
I have a question.
Yes.
So the pseudo-symmetry here will mean that these four dimensions are K3 in some way?
That's essentially what I'm doing, right? So although I'll be looking at it from a non-compact perspective, but if I would insist on compactifying these transverse dimensions, the way to do that would be to make the combined space a K3. That's right. Yes? That's right. Yeah, so one of the things one can do is that, so let's indeed continue this since you're asking this question. So the torus degenerates means that a particular one cycle shrinks within the torus. So it squeezes out a particular cycle, and that cycle could be indeed P times A plus Q times B, could be that particular cycle that shrinks. Now, so what I was mentioning earlier, since we have these M2 branes, let's just go all the way up. Okay. The P, Q strings would actually be the objects that become light at a location where this particular cycle would shrink. And we could call that a P, Q 7 brane. So it's true that, right, so these will be, again, codimension 2. So it will be points on this Z plane. So these we can call 7 branes. And in some terminology, indeed, you could say which 7 brane. Now, if that particular cycle degenerates, then the corresponding 7 brane would be a P, Q 7 brane. The D brane, sorry? Right. So now that if you give yourself a bunch of functions f and g, you can start analyzing what this torus is doing, and then at certain you go to those locations where that thing is equal to 0, and then you start looking at what the torus is actually doing at that location. Then you determine which cycle shrinks at that location, and that tells you what kind of brane you have, the 7th brane you have at that location. And it also tells you what kind of strings become light at that location. Yeah, so f and g depend, at least the functions f and g will depend on the base manifold, which functions they are. Let me mention this at least for those who know. So if this 6-dimensional manifold here is B6, then f would have to be a section of the canonical bundle 2b6 to the power, I think, -3 or -4, and g, maybe it's the other way around, has to be a section of that particular bundle. So which means that these have to be particular functions on that particular space. And if that's the case, then the whole manifold is a Calabi-Yau manifold. Yes? Yeah, actually, to be honest, I'm confused whether this thing, whether I should have written whether the brane would be at z equals infinity or at 0. But at least the reference that I had actually had this as a solution for a 7 brane. And often with these complex notations, people sometimes put things at either at actually there's a way of moving things from infinity to 0. But to be honest, right. I think this is still a correct statement. Which thing degenerates? Oh, okay, good point. That is a good point. Yeah, so maybe I shouldn't have written it like this. This may actually be the solution without putting the zi here. This may actually be the solution of a D7 brane that sits at the point c equals infinity. And indeed, there are other solutions that people write down where they write down something in the denominator. So maybe what I think this is probably a correct, then this should also be a correct statement. In general, actually, it turns out that you can write down solutions for an arbitrary number of D7 branes, and let me just say this. You can in general have this P of z and Q of z. And then the statement is that depending on whether this thing is a polynomial of a higher degree or a lower degree than that, whichever these two has the higher degree, that will determine where the locations of the various D7 branes are. But I should maybe give some references on this. Let me do that at the end of my lecture. I'll give you references on this. Yes. Oh, if there's a limit on the number of D7 branes? Yeah. Okay, good. Let me mention that. So let me where in principle, actually, if you look at these equations, it doesn't seem that there's a limit, but let me briefly again mention the metric of a bunch of D7s. Because it's actually rather easy to give now. I think, is there a 2 or not? Okay. It turns out that you can find the metric of a bunch of these 7 branes in the following way. So it's just a conformally flat metric because it's a metric on this transverse plane where e to the psi is tau 2 times eta of tau to the 24, where tau, to the 4, where tau again is this given function of z, and then you can even do this with an arbitrary number of D7 branes, z minus zi to the power 1 minus 1 over 6. Turns out that this is the, so this was done in a paper by Green, Shapir, Ifava, and Yau. So what this thing actually looks like, say if I take just one brane, this will be 1 up to nf. But for a single brane or around a single 7 brane, what you'll find is that this particular singular behavior where z equal to zi is actually cancelled by that thing because this eta does something singular because tau does something like this near the location of the zi's. So this metric is actually smooth at the location of the D7 brane. So the D7 brane sits here, but this function actually goes to a constant for large if you go far away from the D7 brane. And then you get a conical metric. This is a conical metric when you go far away from the D7 branes. And a cone has a deficit angle. That's the amount of angle that you put in the tip of the cone. And the deficit angle for a given D7 brane is pi over 6. So you can have a maximal number of, so as long as you have nf less than 12, you get a cone. If the number of, nf, n7, if n7 is equal to 12, essentially you get a cylinder, if you like, because the 12 7 branes fold up everything in terms of a cylinder at infinity. And if n7 is bigger than 12, you have a compact space. And if you take 24 D7 branes, then you get the K3. A K3, a compact K3 manifold. A smooth and compact K3. So it's the gravitational back reaction at some level that tells you that you cannot have an arbitrary number of D7 branes. Yes? I'm sorry?
If you have a zero of the discriminant, can you split between P and Q?
Can you determine it at that point? Yeah, by looking carefully at what happens at that point, you should be able to tell you what the P's and the Q's are. Yes? Yes, you can move them apart. Let me go write down a few more examples. So before I briefly do that, because eventually I want to explain where gauge symmetry comes from. Let me just erase this. Let me put that up there. Erase this. So let me do a simple example, not in terms of equations, but in terms of physics, I guess. So indeed, as we'll see later, we'll be able to move these D7 branes apart, indeed, and identify points where something happens, or more general branes. As I mentioned, at the location of the D7 brane, there's a certain cycle that shrinks. And in the case of the ordinary D7 brane, that's the A cycle. At the location of the D7 brane, the A cycle shrinks. So let's do the following. Let's draw a line from here to there. And the reason I'm interested in that line is because I want to start explaining where gauge symmetry comes from. So in ordinary 2B string theory, the gauge symmetry would come from an open string that would stretch from here to there. And we just simply say, well, this open string has an endpoint here and an endpoint there, so it has Gent-Payton indices. And these would be the charged gauge fields, the W bosons of your string theory. The strings that reconnect with each 7 brane would be the diagonal component of your SU2 gauge theory. So this gives a U2 gauge theory, if you like, or SU2 if I only look at the traceless component. But let's try to understand the origin of the off-diagonal components of the gauge symmetry, and they come from the open strings that do this. But there's a useful perspective where I think about the extra torus that's also on top of this plane. And let's keep track of the A cycle. Now, the A cycle shrinks here, and the A cycle shrinks there, because that's what tau does. But here it has a finite size. So I can draw this A cycle as shrinking here, growing there, and shrinking again on the other end. So this combined will give me a 2 cycle, a closed 2 cycle, which is made up of the interval, this particular interval, times the A cycle. It's the cycle that shrinks at the end of the branes. And if I'm still in this perspective that I think about F theory as the torus to 0 limit of M theory, then understanding where this light open string comes from, the string that gives rise to the off-diagonal gauge fields, if I would take an M2 brane on this 2 cycle, this actually will give me the open string that stretches between the 2 7 branes. Okay? Because M theory doesn't have, in this case, open membranes, but it's a closed membrane that gives rise to an open string, because the cycle around which the membrane is wrapping rounds off nicely at those locations. Yes? Yes, we're going to do that. That's exactly what we're going to do. And we're not going to get a 3 cycle. We're going. No, we still get a 2 cycle, but it's fibered over. It doesn't quite fit on a nice interval like this. You have to do something slightly more elaborate. Yes. Okay. Okay. Let me move this one on. So let me briefly finish this example. The basic statement is the following, is that the M2 brane is the open string that stretches between the two D7 branes. The C3 form of M theory. So let me call this two-cycle, let me call it alpha. Okay. So an M2 brane on this alpha will give me an open string. The C3 form, which I can dimensionally reduce over by integrating over alpha, this will give me a one-form vector field. And this is the diagonal component of the SU2 gauge field. And these open strings, or this membrane, is the off-diagonal component. And you can immediately see that these off-diagonal components, these M2 branes, are actually charged because they couple to this C3 form field like this, so they're actually charged under that diagonal component. Okay, now we go to general groups. I probably don't need to remind all of this to you, but let me do it anyway. Anyway, there's this thing, the Chevalier basis of a general group, where if you would have a Lie algebra, so this is the Lie algebra, then you have this Cartan subalgebra, which is the elements H, I in the Lie algebra that commute, the maximally commuting algebra. So all these H's are generators of the Lie algebra that commute. So these are, if you think of it like the diagonal matrices, if you think about the Lie algebra as matrices, at least typically they would be. Then you have the off-diagonal generators, and let me just group them like this. You have plus associated with things we call roots, that the commutation, they don't commute with the individual generators of the Cartan, but they have something like this. So they are the raising and lowering operators, and I think I should have a plus and a minus sign here. So anyway, there are more relations, but this is roughly how we want to think about a Lie algebra. So these things are called roots. And then you have this beautiful story that there's how do you call this? An inner product on those, a killing form on those roots, and you can sort of, and in terms of that inner product, these roots can have, they form a lattice with certain inner products between the lattice generators, and this thing is a matrix, which is known as the Cartan matrix. Which is a thing that has 2 on the diagonal, and it has typically -1s sitting somewhere. So alpha I is equal to 2, but alpha I, alpha j is a number lesser or equal than 0 if j is not equal to I. And I'm just briefly reminding you of this. So there are certain properties that these matrices have to satisfy, but the inner product between the roots that leads to a classification of the possible Lie algebras, because again these Cartan matrices turn out to have again only a bunch of possibilities, and this eventually leads to something known as the ADE classification of Lie groups. So all the groups that you know about fit into this pattern, and we'd like to be able to capture this general type of structure from the string theory. Another useful way, perhaps, and let me be very quick there, to parameterize this Cartan matrix is in terms of these Dinkin diagrams that we know about. And so for what you do for a Dinkin diagram, you write down dots for each possible Cartan, or at least each of these roots, and then you draw a line between them in the case that two roots have a non-zero inner product. And if it's -1, then you draw a single line. So this thing actually, this thing here, 2 dots and a single line here is SU3. A single dot is SU2. And in terms of this picture, one can start thinking about grand unification and other kinds of things by thinking about how various Lie groups are connected with each other. Let me just mention this guy, for example. This guy here would be SO10. And one way in which one can think about symmetry breaking is by saying, well, there's a particular symmetry that gets broken, and then the Dinkin diagram will get broken up into subpieces that would then be the unbroken gauge groups. I'll be coming back to this in a little bit later. But the ADE classification is something that not only tells us about Lie algebras, but it's a particular type of structure that turns out to be directly connected with the thing that I started talking about, namely this kind of geometry. And we want to make a link between this story and this Lie algebras, and that story goes as follows. It's actually a story that has a rather beautiful mathematical it gives a very beautiful mathematical link between what initially seem like very different topics, but they're sort of connected. And indeed, it turns out that there's a thing that we call that in the mathematicians is known as the McKay correspondence, because that thing turns out to be the explanation of why general Lie groups fit into this pattern of F theory. So ADE also classifies. So when we say ADE, we mean this whole structure of Cartan matrices and Dinkin diagrams. The same labeling you could, in principle, apply to various other quantities. It turns out that if you take finite subgroups of SU2, so you have some subgroup which is a finite group of SU2, and the classification of finite subgroups of SU2 also turns out to follow this same ADE pattern. So for every group, Lie group, there's a corresponding finite group of SU2. And then there are also things we know as singularities, which I'll write down in a second what they are. They also fit in an ADE pattern. And there may actually even be other things. But we're actually going to precisely connect these two things, indeed, with the Lie algebras, because we're going to show that there's a connection between these two quantities and indeed gauge symmetries with the corresponding ADE Lie group. So this McKay correspondence indeed partly essentially is about this correspondence. So what you can do is the following. I could take a particular subgroup of SU2, and SU2 acts on the two-dimensional complex C2, so that's how it acts as a matrix, and I can divide it out. So this is an orbifold, if you like. And it's a space that's known as an ALE space, asymptotically, locally Euclidean, not to be confused with ADE. but it's still kind of connected. And indeed, you can think about this because this is a non-compact space as a non-compact version of one of these ADE singularities. And we're going to show that that leads to that type of gauge symmetry in a second. So let me tell you what ADE singularities are. We'll just give you the equations for now. So there's a class known as AN singularities. Now the AN groups are the SUN group. So this is SUN plus 1 in terms of the Lie algebra. But there's also a singularity associated with it. And what's meant by a singularity, it's indeed an equation that looks a little bit like the equation that I had before. It looks a little bit like that, but in this case, not quite yet. X squared plus z to the n plus 1. This is known as an AN singularity, and it's a Zn orbifold singularity. The Lie group, discrete group of SU2, this gamma in this case is just Zn. Actually, Zn plus 1. And indeed, it rotates. You can see that this has a Zn plus 1 symmetry. Let me skip the dn's. There's also a dn series. Let me write down the E6. Seven. E8. X cubed plus z to the 5th. And as you can see, so what these singularities are, they are basically, one way of thinking about it in the terminology that we just established to some extent, is that you can think, these En equations in particular, they all look like this. As you can see, actually, they're pretty high powers of z. So these polynomials have some pretty high degree of vanishing at z equals 0. So indeed, this delta quantity that I guess I erased, it's probably down here. This delta quantity indeed will go to 0 with some pretty high degree at z equals 0, which indeed means that this torus that's associated with this particular type of equations does something pretty singular at z equals 0. So, and that's why these things are called singularities. Now, the thing that you would want to do if you want to study what that singularity looks like, you want to sort of resolve that singularity. You want to at least separate things out a little bit. So here there's a high degree of 0, again, if z goes to 0. So one thing that we could do in the case of this AN singularity, we can resolve it by just separating things out a bit. So you resolve it. And for the Zn, what you would do you would write it like this. So you introduce some numbers, zi, and rather than putting all the zeros at z equals 0, you separate them out like this. And indeed, it turns out that the zi's are the location. You can think about them as the locations of the D7 branes. Okay. Now, one of the consequences of this is indeed that if you study this particular space, you indeed discover that if I have these Zns, all these Zi's, and I put them here, Z1, Z2, etc., that they're indeed going to be connected by two cycles in the way that I explained for the Z2, for the A1 singularity for the Z2 group. So what turns out is that this particular singularity and all these other singularities, once you resolve them, you can recognize that they have certain finite size 2 cycles. The size of those cycles indeed will shrink back to 0 size if you take all the zi's on top of each other. And that's the point where the gauge symmetry will get restored.
So the number of these separates is now n+1.
Yeah, so let's get all this straight. So an is SU n plus 1. So for an an singularity, you get n plus 1 branes.
You mentioned just now that if you have 24 P7 branes, you get a K3, right? So K3 has an AB classification. So in this case, do you have 24 P7 branes or just n+1?
So your question is, can n be bigger than 24?
Or whatever number that's not 24, right? Now we have n for some number that may or may not be 24, right? So
Yes. So if I look at things locally, if I only keep track of what this torus is doing, then this thing can be much bigger than 24. And for a long time, I actually thought that if you do things with D7 branes, that you cannot have more than 24 D7 branes. But it turns out that there are certain limits. At least if you let's say this way, the deficit angle is only something that builds up if you're far away from the D7 brane. The region around the D7 brane is still pretty smooth, and the deficit angle is not yet built up over there. So I think there are situations where you can consider more than 24 D7 branes if you do everything locally, as long as you don't are not extending the metric all the way off to infinity.
So let's suppose if you want to do FU by gut, then it's not even
Then it's not compact, but then it's just like one of those cones that I was drawing, and then you have to compactify it somewhere else. So it's luckily at least that guts don't have ranks of gauge groups that are beyond 24, for sure, at least. Let's assume that that's a thing that we were happy with. Okay. So now let me just make a few statements that will tie all this together, that initially at least are mathematical statements, and then we'll think about them a bit from a physics point of view, and that will explain where the gauge symmetry comes from. So the math will tell you that of course, you can resolve a singularity, and the theory of how you actually nicely resolve these singularities is roughly the same idea as here, but anyway, it's a bit more subtle, so I will not go into those details, but you can imagine that you can do that by generalizing that polynomial by including lower terms. One then can identify of 7 branes. Mathematicians wouldn't use that terminology, but it's just singularities on the plane where delta is equal to 0. The 7 branes are connected by 2 cycles. Let me call them alpha I. And what I mean by are connected, I'll be a little bit more specific about that in a second, and also be a bit more specific about what these 7 branes are. This goes back to this discussion of the P, Q 7 branes. But let me make the following statement, that now those 2 cycles within this 4-dimensional space, so this as a whole, this is a 4-dimensional space, which is this 2 torus over this complex plane. In that 4-dimensional space, there are going to be a bunch of 2 cycles, and those 2 cycles can intersect with each other. 2 plus 2 is 4, and therefore two cycles have one single intersection point, or a couple, or zero, but at least they can intersect at a certain point. And you can keep track at how many points they intersect, and that gives me an intersection form. And it turns out that, and I hope I get the sign here straight, that alpha I with alpha j, in this case, is minus the Cartan matrix of that particular ADE group. So I start with a certain ADE singularity. You resolve it. You're going to identify locations of 7 branes, and you connect those with certain cycles, which becomes 2 cycles, and it turns out that one can prove that those 2 cycles have an intersection form, which is that particular Cartan matrix. So that's the connection between the ADE classification and the singularity. What's important here is indeed that there's sort of essentially an isomorphism, because this class of 2 cycles forms a lattice, and there's an isomorphism between the set of 2 cycles of this resolved singularity and what we call the root lattice of the corresponding Lie algebra. So that's certainly a first hint that these things might be connected, that this whole duality actually happens. So let me go erase this and then make a few physics comments about this. So the physics as we mentioned before, we can have a P, Q 7 brane which is associated with the torus degenerates such that the P times A plus Q times B cycle shrinks. Now, at this P, Q 7 brane, the P, Q string becomes light, because that's the that will be the brane, the membrane wrapping that particular cycle would become sort of tensionless, or at least, yeah, essentially it would become light. So that's one remark. If I now take 3 branes, and someone was already anticipating this, so I take 1 brane here, 1 7 brane here, another one here, and another one there. Then what you can have is you can have a P, Q brane string, becoming light here, another P, Q with a different P and a Q becoming light here, and a third one here. And typically, actually, it turns out that if you take 3 branes for which the sum of the P and the Q's adds up to 0, then you can take the corresponding P, Q string. So this is P1, Q1, P2, Q2, P3, Q3, and you can join them together if the sum of the P's and the Q's add up to 0, assuming that I give them an orientation like that. And what I mean by this in terms of the geometry is that let me take 3 7 branes, the locations of where these singularities occur, and I connect them just by a line like that. But now I look at the corresponding cycle in the torus, and I can draw the cycle in the torus which shrinks here. It starts growing here. The cycle that shrinks here starts growing there. And the cycle that shrinks here starts growing here. And because of the junction condition, those 3 cycles combine into a nice cycle. They add up to something that becomes a 2 cycle that looks like that. Okay? So the singularity indeed has a bunch of these two cycles associated with them. And again, I can wrap a membrane around it. Again, it becomes light in the limit where all the branes are on top of each other, and it gives rise to the gauge boson. And because of this algebraic relationship between, or at least the isomorphism between these cycles and the root letters of the Lie algebra, if you start thinking about it a little bit more, it's quite clear that the non-abelian gauge bosons will group together into, again, a bunch of diagonal gauge generators which come from the C3 form, and a bunch of diagonal generators, so you really get the ADE gauge symmetry out of those degrees of freedom.
Where do the gauge bosons live? I mean, obviously in the 3 dimensions, but I'm having trouble seeing how all of this, maybe I'm just...
Okay, so where do they live?
I'm looking at SU4, so I should see something like 15 gauge bosons living somewhere.
Yeah, so the number of gauge bosons, so the question is there two types of things you want to keep track of. How many gauge bosons do you get? How many you get depends on how many 2 cycles you have. So that's for every root of your algebra, there's a charged generator of your Lie algebra, and therefore, or at least, yeah, and there's a corresponding membrane that can wrap a cycle that will give rise to that particular Lie algebra. But I try to, indeed, that's why I have that original blackboard up there. So everything I've been talking about only took place in the 8-9 dimensions, actually. So that's the complex plane that I've been talking about. So eventually, if you ask me where do they live, actually they all live in one point, which is the point z equals 0.
Sure. But they also, I mean,
because in the limit where I take the singularity, then at the point z equals 0, that's where all these little infinitesimal cycles live.
Where does the space-time index come from?
Oh, where does the space-time index come from? So at the moment, I'm just telling you, well, there's a membrane which becomes a string after wrapping it around a circle.
This weird set of cycles or something, right?
Right. So if you want, you can think again back about the SU2 example. There I have the membrane wrapping that particular cycle, which just becomes an open string but stretching between the corresponding D7 branes. And then by quantizing that particular open string, I can find that it has space-time indices. It has to be an n equals 1 multiplet in 4 dimensions, and it's a gauge multiplet. It includes a gauge multiplet. So in this case, it's the M2 brane that you can first dimensionally reduce. If you want to get these exceptional gauge groups, you have to accept this particular point of view, that the degree of freedom that you actually have to quantize is not just a fundamental open string, but it's one of these funny, this is called a junction. Where a P, Q strings, these non-perturbative type of strings, are connecting with each other. But in the end, at least from the 5-dimensional perspective, you can still think, or at least from the 11-dimensional perspective, you can still think about it as a membrane wrapping that particular cycle. Yes?
SU2 example, is that SU2 or U2?
I focused on the SU2, the U2, the U1 part would just be the overall motion of the 2 branes. Often, actually, in the singularities, in the study of these singularities, one has the restriction. I erased that thing here, but it's here. Or at least I did, maybe I didn't. One has the restriction that the zi's sum to 0, so you try to decouple the overall center of mass motion, which is like decoupling the U1.
But if you separate the 2 singular points, do you get a U1 squared or you get
In principle, you would get U1 squared, I would say, yes.
so it's UN, there's always a U1 factor.
There's the U1 that's always there. Although, by the way, the U1s will actually play a bit of an important role in some of this story. But very often those things become massive because of coupling to more fields. But
Are the positions of these singularities, are those moduli? Are they free to move these?
locally they are. So they are indeed, literally they're called moduli of the singularity, at least of the resolved singularity. These ZIs, you can just locally move them around. However, and I briefly mentioned this, is that if you have this type of singularity, there are topological or at least geometrical restrictions on what kind of functions you can write down there if this is to become to be a compact Calabi-Yau manifold. So if I want to put this on a compact space, then sometimes those locations indeed are not free to move.
And so by moving them apart, that's like Higgsing, right?
That's like Higgson. I would actually say in many cases those things would not be parameters. And for example, in the case of where the geometry is what I was drawing earlier, you definitely want to remove those parameters because you want to argue that you have to sit at at least at the symmetric point where you want to sit.
Well, I just have a question because we understand in some way in AN they are easy because this is just the seventh range if you have to do n.
Right.
It's just not, well, of course, D6 is very complicated. But for example, if I look at the simplest example, which would be D4, SOA.
Yeah, the next non-simple.
What actually would be the things? Is that worked out?
Yeah, I can give you a quick, let me end there and I'll give you a quick list of the type of things that one needs. And then I'll stop. So what people have worked out is sort of, once you resolve these singularities, you can recognize what kind of 7 branes you need. And let me briefly introduce 3 types of 7 branes. So I mentioned that's the D7 brane, corresponds to this particular transformation. So meaning that around the D7, that's what happens if I move tau around. But now if I move around another type of brane, I could have other transformations which also involve the S transformation. So let this be the T transformation, tau to minus 1 over tau, which is the S-duality transformation. So terminology you can use is an A brane is indeed associated with the transformation T. A B brane is associated with the transformation ST squared. And it turns out that in terms of this P, Q language, this is a 1 minus 1 brane. And in terms of the transformation that you get here, the SL2Z transformation for a 1 minus 1 brane, in general for a P, Q brane, this SL2Z transformation looks like this. 1 minus PQ Q squared. So this is my notation. So this is a B brane, and then there's one other type of brane, the C brane that one introduces, which is T squared S. And this one, I think, has numbers 1, 1. So in terms of that terminology, these are 3 classes of branes. And since the C brane and the B brane involve this transformation S, they're really non-perturbative branes. And the kind of strings that become light on them are these bound states of a D string and a string. And then in terms of these type of branes, it's possible to separate out these singularities so that the only remaining singular points are these individual fundamental branes. And it turns out that, okay, as you said, AN in that case is simply this A brane to the power n plus 1. Dn for n bigger or equal than 4 is A to the n b times C. E6, 7, 8 is A to the power 5, 6, or 7 times b c squared. I'm not sure what exactly one would learn from this, but this tells you what kind of kinds of brains you would need. You would need these B and C brains to build the Lie algebras that are not the classical Lie algebras. Let me, okay, yes? Yeah, that's actually an interesting question. Can one think about the B and this particular D combinations as a situation where one not only has D7 but also an O plane, O7 plane? So I think you're probably right that one can think about this thing as some kind of bound state, or at least some thing where O planes and D7 branes are on top of each other. Sorry? Sense paper discussed that? Okay. In the classic paper where and that's a limit indeed where again, at some level, the whole F-theory technology becomes a bit redundant, because you can do things in terms of just the 2B string theory with O planes.
What about the SP groups? Or I mean, any of the other exceptional, like the F's and the G's and all those? Presumably you can build those too.
Yeah, I thought there was, yeah. So the F's and the G's, I'm not familiar with at all. The SPs, again, I would give the same answer, that probably from thinking about it from the orientifold perspective, it's probably the way to go there. But I'm not even sure where at least they're part of the D. Yeah.
Only these simply laced groups.
These are the simply laced groups that would fit in there. The SP would not. But at least in terms of the way of constructing them out of string theory, they sort of fit a little bit in that category. But now for grand unification, for example, again, SO10 and in some indirect way E6 and SU5 obviously are useful, are sort of the central groups. I should say that even if you do work with SO10, the fact that we want to be able to build, and this is maybe the last comment that I make, is that if you want to add matter to it, so up to now, actually, today I only discussed how do you get gauge symmetry. You also want to be able to add matter. And for example, you want to have a 16 a representation that's charged on the SO10, which is transformed as the 16. And the way you would actually do this, and let me briefly mention this, is what you would do is you would take an SO10 singularity and you would intersect it with some other singularity in such a way that locally at the intersection point that the singularity gets enhanced to an E6 singularity. And this comes back to, again, for example, this story with the Dinkin diagrams, that if I take SO10, which is this part of the Dinkin diagram, and extend it to E6, indeed what happens is that locally there will be a solution to a Dirac equation which you can think of as being a massless mode. So it's a Dirac equation that will tell you whether or not there's a massless mode that lives on the intersection of the two branes, which is the location where locally this singularity suddenly becomes a bit more singular. It gets an E6 singularity. And by thinking about it properly, you can see that it transforms in such a way under the symmetry of the SO10 as it would as the adjoint of E6 would decompose into the SO10 representations, and that gives you a 16. So I guess what you want to take away from this is that if you want to really do grand unified model building, then you definitely want to have some control over these exceptional Lie groups in terms of how to make the degrees of freedom, etc. Yes? What is the advantage? I think that, there's still essentially differences. Although I went back to the M-theory perspective as a way of explaining why there are certain light degrees of freedom, and also because it gives a nice SL2Z covariant frame. Our degrees of freedom are still the 2B string degrees of freedom. I guess one advantage of working with F-theory is precisely that this particular 2 torus that we've been using to get the M-theory perspective is very useful, but actually its size is much less useful than its shape. And what's clever about F-theory is that we just trade the size of the 2 torus for a whole extra dimension. And what else can you do if I would be able to give you an extra dimension? You would take it. You can do many good things with it. Okay, so it's time. So let's have a break, and then we can reconvene it.